Alright, silly people, here's the situation. We have a right circular cylinder, so a cylinder, um, that is going to be our waveguide, and we're going to be propagating T, M, and TE modes through it, and calculating what those fields are going to look like, as well as getting our cutoff frequencies, and then also getting an attenuation constant for the cylinder. So, um, So we're gonna start with the TM modes. When you do that, you have to start with your longitudinal electric field. That is the electric field that's pointing along the z-axis. So you're gonna have a decay piece, which is minus I omega t minus kz, uh, and then you're gonna have your expansion. So starting with L equals 1 to infinity, sum over m equals 0 to infinity. Um, it's going to be dependent on Bessel functions, which are functions of gamma Lm, gamma Lm, so that you can set your um, boundary conditions. It'll be um, explained in a second. So, and then you'll have your phi dependence, which is going to be some constant dependent on L and M of e to the im phi, and then some other constant blm e to the minus im phi. Um, so gamma lm is just being the xml over r, where xml is the lth root of the mth Bessel function. That way, when you set your rho equal to r inside the Bessel function, um, you just get that the whole thing is 0, which is what we want for our boundary conditions. So awesome. That's our longitudinal electric field. We can get the transverse electric by calculating ik over gamma squared, transverse gradient of the electric field. I'm going to go ahead and look at the L equals 1, M equals 0 term, which is the lowest order in the expansion. So I'm going to quickly rewrite the longitudinal field with that in mind. I omega t minus kz, you'll have the 0th Bessel function as a function of gamma 1, 0, and rho. And then some constant a. Actually, it's not phi dependent because m is set equal to 0, so that's really all you need. But also just some constant a thrown on there. Okay, transverse electric field is the transverse gradient of that. When you're in cylindrical coordinates, the transverse gradient is going to be equal to d rho in the rho hat direction, and then d phi, or 1 over rho d phi in the phi hat direction. So no phi dependence here, so we just need to take the rho derivative. So that's going to look like ik over gamma squared e to the minus I omega t minus kz. You have your constant a, then you're doing the rho derivative of the 0th Bessel function, gamma 1, 0 rho. I mean, that's a derivative that has a known form. It's also going to be in the rho hat direction, so I might as well specify it now. That derivative evaluates to having a rho or a gamma pop out, and then it will raise the m to 1. So it's now the first Bessel function as a function of gamma and rho, the rho hat direction, and it flips the sign. Don't forget the sign flip. So that simplifies. You'll have one of the gammas cancel out. So you have minus ik. I'm going to stop writing gamma 1, 0. I'm just going to start writing gamma. You have e to the minus I omega t minus kz A J1 of gamma rho in the rho hat direction. Awesome. We can get the transverse magnetic now, which is going to be mu epsilon omega over k z hat cross e, and then that's going to be et. So z hat cross rho hat is just phi hat. So you're just going to end up with minus I mu epsilon omega over gamma 1, 0, which is gamma. You'll get your decay piece, omega t minus kz. You'll get your constant A. You'll get your J1 of gamma and rho, and it's going to be in the phi hat direction. And there you go. So those are all of your radiation fields. If you want to look at your frequencies, generally the frequency is given by the square root of gamma squared plus k squared over mu epsilon. So you could get your omega 1, 0 from that. But specifically, I think we're looking for the minimum frequency, which can be found by using that same equation, but in just letting k go to 0. So you're going to have gamma 1, 0 over root mu epsilon. And so gamma 1, 0 is going to end up being just the x0, 1, so the first root of the 0th Bessel function, over r, and then mu epsilon, and then you have your frequency in terms of stuff that are just in the problem. Okay, that's the TM modes. We can look at the TE modes now. And with TE, you have to start with the longitudinal magnetic field. But it's going to be a very similar wave function as before, minus kz. So you have your decay piece, you have your expansion, now starting with m being set equal to 1 because boundary conditions, and then jm, gamma lm, rho, ALM e to the im phi plus BLM e to the minus im phi. Okay. Where gamma LM means something different in this case, now it means x prime ml over r, where x prime ml equals the it's the elf root of the derivative of the mth Bessel function. Right, so the boundary conditions for a magnetic field is that the derivative goes to 0 at the boundaries rather than the just itself goes to 0 at the boundaries. So that's why we start with m is equal to 1, and that's why we have x prime now instead of x in our definition of gamma. So that's our wave function, and now the minimum value for L and M in the expansion are both 1. So the lowest mode is that L is equal to M is equal to 1 mode. So we can look at that mode specifically and then write out what BL is in that case. E to the minus I omega t minus kz. We have the first Bessel function as a function of gamma 1, 1, and rho. We have A e to the I phi, and we have B e to the minus I phi. Cool. We can get the transverse magnetic fields now as being I k over gamma squared, transverse gradient of the longitudinal magnetic field. But we have phi dependence and rho dependence now, so that's going to be a little bit more of a process. So ik over gamma squared e to the minus I omega t minus kc. Split it into a rho direction and a phi direction. We have that it's a e to the I phi plus b e to the minus I phi times the rho derivative of the first Bessel function. And then the phi direction, you're going to have the first Bessel function and then over rho, and the phi derivative of the phi dependent stuff plus b e to the minus I phi. Right? So we can calculate those now, just writing out the prefactors again. Ik over gamma squared e to the minus I omega t minus kc. And then you have that the rho derivative of the first Bessel function is gamma over 2, and then times the difference between the 0th Bessel function and the second Bessel function, right? And then the phi hat bit, you'll end up with the first Bessel function as well as that's over rho. And then that derivative is just I times a e to the I phi, now minus b e to the minus I phi. Okay, that's your transverse magnetic. Then your transverse electric is going to be the mu epsilon omega z cross that, right? Yeah. Mu epsilon omega or k z hat cross bt. And essentially what that cross product is going to do is going to make your phi component replace your rho component, and you're going to have minus your rho component replace your phi component. So you're going to have I mu epsilon omega over gamma squared times z hat. Actually, I'm just going to go ahead and do the cross product. You're doing the decay piece, and then you have that it's J1 gamma rho over rho times I a e to the I phi minus b e to the minus I phi. And then your rho component is still just gamma over 2 a e to the I phi plus b e to the minus I phi j0 of gamma rho, and then minus j2 gamma rho.
Be careful, silly people. You're actually meant to throw a minus sign onto the phi component in this case. That's just how the cross product works. So you'll have J2 minus J naught instead of J naught minus J2 there.
Okay. That'll do it for the radiation fields. We can get our cutoff frequencies in a similar way, where now we're going to have that the cutoff frequency omega 1,1 is equal to 1 over mu epsilon, and then we'll have gamma 1,1 up top, which is going to be x11 prime over r root mu epsilon. And again, you can like look up what the first root of the first derivative of the first root of the derivative of the first Bessel function is. And so we're good there. Now we need to calculate the attenuation constant, and for that I'm just going to use the TM mode and assume that it's going to be the same for the TE mode, but take that with a grain of salt. Um, Generally, the attenuation constant is 1 over 2 times the power times the derivative of the power with respect to z, which is physically that's just the loss of the power as you move along the waveguide. Um, and it doesn't actually mean a derivative with respect to z because it's not going to be z dependent anyway. So uh, the power then is what we need to calculate, which is going to be omega k over 2 gamma squared uh, epsilon, and then the surface derivative, or surface integral, I should say, of the square modulus of your longitudinal electric field. Okay, so again, we're doing the TE modes, so specifying that we're in the L is equal to 1, M is equal to 0 mode. We have omega k epsilon over 2 gamma squared. And then the electric field that we had before was just, it was like A J0 of gamma rho, and then we had the propagation piece. So minus I omega t minus kz. We're taking the square modulus of that. And then the area element is rho d phi. No phi dependence, so that phi derivative is just going integral is just going to be 2 pi, so we'll go ahead and factor it a pi omega k epsilon over the just gamma squared down here. And then when we square this, the decay piece is going to go away because it's a square modulus. You'll have to take the complex conjugate and multiply it by the self. You'll get a squared up front, and then you're just doing the rho derivative from 0 to r of the rho j0 gamma rho squared. And then this integral is a little bit silly, and I did just kind of look it up, but it ends up being gamma squared. Oh my gosh, it's a really gross gamma. A squared, then you're doing gamma squared over rho squared over 2. And then you'll now have the first Bessel function instead, and it is squared. And you're evaluating it from 0 to r. That's going to evaluate to just having a r squared, a squared up top, and then gamma squared with a 2 on bottom. And then now it's just time this j1 gamma r squared. Okay, now the power loss on the walls with respect to z will be 1 over 2 times the conductivity times the skin depth times the permittivity of the walls squared. And then times the closed loop integral of the n hat being the vector normal to the surface of the wall, so it's going to be rho hat in this case, crossed with the magnetic field on the wall, and you square it, and then you're doing a line integral. So our magnetic field, let me go and grab it actually. Magnetic field was this thing. So taking the square modulus of that is going to be fun. So we're doing 1 over 2 sigma delta mu squared closed loop integral of, we're going to have I mu epsilon omega over gamma e to the positive I omega t minus kz aj1 gamma rho. And then you're going to have minus I mu epsilon omega over gamma e to the minus I omega t minus kz aj1 gamma rho. And you're integrating that over just phi now, actually, d phi. Again, there is no phi dependence in this, so that's just going to evaluate to 2 pi, that integral. But then the complex, the square modulus, I'm going to go ahead and write pi over sigma delta mu squared. Square modulus is looking like mu squared, epsilon squared, omega squared over gamma squared. The propagation pieces will cancel out. You'll have a squared, and you'll have j1 modulus squared. And that's going to be actually of r because it has to be the magnetic field at the surface. So that is also of gamma r. Right. And then so this is gamma r. Okay. So finally we can calculate the beta, then the attenuation constant. So it's going to be 1 over 2 times the power. So multiplying the power times 2, and then flipping it, we have gamma squared j1, actually the j1 will be on the bottom, so it's just gamma squared up top, and then pi omega k epsilon r squared a squared. I think I forgot a factor of r when I did the, yeah, because the line element for cylindrical coordinates you would multiply by r. So that's the difference there. So that's going to be r. Not there, actually. There'll be an r here. Okay. So what was I doing? Okay, yeah, I was saying a squared j1 gamma r squared, and then minus dp dz was all this junk that we just wrote down. So pi r mu squared epsilon squared omega squared a squared j1 gamma r squared, and then over sigma delta mu squared. So that's a lot of terms, but we do get a lot of things that cancel out. So the Bessel functions are gone completely now. The gammas should be as well, because we had a gamma squared on the bottom of the dp dz term. So gammas are gone as well. Pi is gone. You end up with a 1 over r. So r on the bottom. You end up with no power of mu. You end up with an epsilon up top, as well as an omega k. Actually, there's no term that involves k on the top, is there? So, no k. There's going to be a k on the bottom, though. And then the a squareds cancel out. So then now it's just, we had sigma delta, 1 over sigma delta. Now I'm just making sure I got that right. Um, yeah, sure. Okay, that's going to be your attenuation constant then. Um, we can take it a step further. So I did this all in the TM10 mode, um, but we ended up with a attenuation constant that's going to be universal to this um, waveguide. So we can actually now calculate, we can plot beta versus omega. Um, and to do that, we're going to change the form of this equation so it actually reflects like the minimum frequency. Um, Remember, the minimum frequency is going to be given by gamma over root m mu m, no, mu epsilon. Uh, so solving that, you're going to have that gamma squared is equal to mu epsilon times the minimum frequency squared. Um, and you're going to have that the frequency in general is going to be uh, gamma squared plus k squared over mu epsilon. And then you can solve that for k. So you can say k is equal to the square root of mu epsilon omega squared minus gamma squared. And then you can plug in this form of gamma into this form of k. So we're going to end up eliminating the wave number from our attenuation constant completely. So that's going to be mu epsilon omega squared minus mu epsilon omega bar squared. So, I mean, now you can just plug this into our attenuation constant. So we're keeping the 1 over r sigma delta. We get to have epsilon over root mu epsilon. So that's going to be fun. And then omega over the square root of omega squared minus omega bar squared. So we can simplify the prefactor by a bit. So it's r sigma delta just square root of epsilon over mu now. And you want to factor out an omega from the denominator. So the omegas will cancel out and you'll have 1 over square root omega minus omega bar. It's actually 1 minus omega bar squared over omega squared in that radical down there. One more thing, there's a general form for the minimum skin depth for the minimum frequency, where given by omega, or not, delta bar. So the minimum skin depth is going to be the square root of the frequency over the minimum frequency times the given skin depth. So making that substitution, we'll have r delta bar sigma will have the square root of epsilon over mu. You'll have the square root of omega over omega bar. And then you'll have 1 over square root 1 minus omega bar squared over omega squared. And now you have it as a function of omega over omega squared, or omega over omega bar. So that's fun. So if you then want to plot your attenuation constant versus your omega bar over omega, then you're going to end up with it's going to come down from infinity down to some minimum value, and then curve away pretty much linearly once it reaches that. That's just a rough sketch. So yeah,